It's 2:34, 4 minutes too late. I'll leave it up to him. In addition to the excellent moderation that he does, Professor Udit Bhatia is a very well-known emerging researcher in areas at the intersection of water, infrastructures, climate and ecology. The core of it is civil and environmental engineering. He is at the Indian Institute of Technology, Gandhinagar. So after when he joined his PhD, he said, from the start he said, there's one thing I want to do, one thing only, to go back to India and become a faculty at one of the IITs. So he got his job at two IITs, Indian Institute of Technology, Bombay, which is sort of the oldest IIT, and IIT Gandhinagar, which is one of the newer IITs. They made it very attractive for him and his family, and also it shows his northeastern background, right? I mean, we are new, we are young, we'll create new history as opposed to here's this old, place which just builds up reputation, right? So that's where he is, and some very excellent work in many different areas. I would like you to take, so he's going to give an introduction to climate, and then he's going to go step by step in helping you understand how models are built. This will help in your assignment, in the first assignment that you have with Kerry Emanuel's book, but also others. Also in other ways. There will be some intersection with what Danish explained, but that is more initial, to just get you oriented in the field. This will go a little bit more, you'll see, slightly more towards the science of climate. The science and maybe the engineering, but mostly the science of climate and modeling of climate. So again, there are war game teams and they exist for a reason. Some of you will probably relate to this much more in terms of your background and interest. Some of you will feel, okay, this is more of the science that I have seen, which is okay. In some other lectures, including the one at IIT with Professor Joshi Roy and some other lectures you'll see there, or other kind of work you do, it probably more on, let's say, on the economic side, or the social science side, or the engineering side, or different sides. So that's the whole essence of climate as a grand challenge, and you need to collaborate with each other, right? So most of the collaborations you will do will be as part of your war game teams, except this first assignment, which is, as I said earlier, which will be through the roles that you have. So scientists across these war game teams, engineers across these war game teams, and that is because the way this book is organized. And as I also said, Professor Kerry Emanuel is now emeritus faculty. He is very good, one of the top scientists in the science of climate. So in terms of credibility, and as I said again, irrespective of however, biggest scientist ever and whatnot, the most consensus, you should always question. Science progresses through questions and skepticism. Not denialism, but skepticism. There's a big difference between those two. So you should always question and things always improve. But then again, if you think of his expertise, this book tries to cover a lot of things, all the way from science to some engineering, policy, economics, etc. Professor Kerry Emanuel is not the expert in economics and policy. So you'll probably find a little bit more to critically evaluate there compared to the science. But even in the science you might find something. And I want to hear your perspectives on those in addition to what he teaches. So in your presentation, both in the slides and in the video, emphasize first of all what he has said in those two chapters. Right? That's for your own education and for everybody else. And then emphasize your personal critiques, whether they are scientific commentaries, whether there are other things that you have read, and so on. And to balance some of the economics and social science side, that's why I said, for those chapters especially, one other thing that you should read is the Eco-Modernist Manifesto. I suggest all of you read that. It's not that bad, but that's one other thing. And feel free to read other things and cite them, whether it's papers, whether it's assessment reports, and so on. So this will take us one step further into that science and into how modeling is done. A lot of climate science and assessment is based on models, because we're talking about things that may be, all the way from seasonal to, sub-seasonal to seasonal, to interannual, to decadal, to multi-decadal, to century scales and beyond. Okay, so it's important to understand models which can help us take a look at the future, even though it is sometimes a probabilistic look, sometimes like it's what if scenario planning, but it's important for us to understand. Okay? Danish, you were supposed to introduce Professor Udit Bhatia, you said no. Anything else that you're going to add? I have to put it in the spot there because he said he's not ready.
No, I will just add only one point, that if you can engage with him in the discussions, then you'll get a lot of perspective on the same thing. That's the one thing that I enjoyed a lot when I used to discuss with him.
So what it means is just from his lecture you'll not get much. But if you only listen.
No, I'm not talking about this.
So over to Udit. Take us. Take it over.
First of all, for having me here. We have
This one.
This might be a bit difficult, but I'll try my best to use it.
Yeah, but that is just for the camera. His voice will not.
I think if you speak like this, all of us can hear, right? Including the audio video sounds. Yeah. So it's up to you what you want to do.
I think without mic it would be easier. I would be a bit louder. So thank you for having me here. First of all, I mean I'm of course a bit tired because I had a total sleepless night. I was in flight, but I'll try to make sense whatever I'm speaking. But if not, please feel free to correct me, step in. Let's have this as an interaction. Husky and an SDS lab alumnus, right? And I owe a lot to Northeastern and of course SDS. And this is one very small attempt to give something back to my alma mater. But more than that, I'm here to talk about something I've been really passionate about for last 1 decade. I think I was talking to Arup a few days back. It's exactly 10 years when I joined Northeastern University. It was 2014. Today we are in 2024. In last 1 decade, I have learned a lot and realized that still a lot has to be learned in this area of climate science, policy, engineering, translation, where my lab tries to do some of these things. At IIT Gandhinagar, I lead this lab called Machine Intelligence and Resilience Lab, which tries to bring machine learning together with network science, together with physical-based models to improve the understanding of Earth system processes, as well as resilience, specifically focused on various systems within India and by extension to Southeast Asia. So with that, I'll start my lecture on climate change science. And what I'm going to cover today, I have tried to keep things very simple, but if you find anything that requires repetition, if you want me to repeat anything, please feel free to stop me there. I would be more than happy to help in whatever way possible. So we'll start with a bit of a scientific discussion that why we should care about climate change with some numbers, certain questions that I would request you to answer as we go forward. Then I'll give you a 30,000 feet overview of climate system, what we call as bird eye view. I call it as a 30,000 feet because that is the height or elevation at which the majority of atmosphere ends. So if we understand what's happening in first 30,000 feet, we understand a lot about Earth system processes. So we'll typically focus at that scale. And then we will design our first climate model today. So you would be hearing this word CMIP, climate model, GCM, scenarios. Today we'll take first concrete step in designing your own climate model, which is actually used, which has been used in various scientific studies, endeavors, and now we have computation, but it has to start from somewhere, and it started from zero-dimensional models. Yeah.
Just a note, please make sure to take notes on this. And as I was saying, for some of you this may be more aligned with your background, for some of you it may not be. Please expect both individual and work in team level assignments. That being said, I'll be fully understanding of the fact that you have different backgrounds in terms of grading your assignments. But each of you should try to take something out of this. So please take copious notes.
So first thing first, that what is climate, how it differs from weather. You might have heard, climate is what we expect, weather is what we get, right? But interestingly, it is not as simple as it sounds. Okay, expectation is fine, what we get is fine, but climate is essentially a system that accounts for atmosphere, its coupling or interaction with various processes that are happening at ground level. And when we talk about atmosphere, I am essentially focusing on first 10 kilometers, first 30,000 feet of anything above Earth's surface. So your plane flies at 30,000 feet, exactly at the boundary of the inner atmosphere and outer atmosphere. So that is going to be our area of focus. And of course, when we talk about weather, we talk about short-term changes. That it is raining today, it will not be raining tomorrow. I am not talking about climate, there I am talking about weather. It's a short-term change that we are essentially talking about, and that's exactly what we get. That's what we also care about a lot. But when we talk about climate, we are talking about behavior that is average over a long period of time. For example, when I say that summers are usually warmer than winter, I have made a statement about climate. Right? If I talk about any specific day that 30th June was warmer than 29th of June, I am talking about the weather of that particular location in that specific area. Right? This distinction would help us a lot, because sometimes when we try to talk about climate, weather, and we often forget this distinction, and then we try to confuse each and every extreme event being attributed to climate change and this and that, and that's where a bit of a caution is needed. As Arup mentioned, bit of skepticism is needed, and that's where this very small definition does help us a lot of time. If we talk about a climate system, I'm sure Danish must have shown it, but we are not going to deal with all the components, but essentially it's one source of energy coming to us, getting distributed to various components, be it hydrosphere, where most of the water resides, be it cryosphere, where a lot of our ice resides, be it biosphere, where most of the life takes place, thrives, and so on. But interestingly, all these components are talking to each other. They are tightly coupled with each other. Whatever changes are happening in the ice component, they are impacting the hydrological component. Whatever changes are happening in water or hydrological component, they are impacting life on the biosphere. And that is where it becomes a very interesting puzzle for us to solve, right? Think of it as a multi-piece puzzle where all things have to fall rightly in place before you can see a full picture. And that is also one of the big challenges that come when we start talking about climate change and so on. Now, interestingly, climate is always changing. Our expectation is also changing. Although I said climate is what we expect, that expectation is also not same. One very simple example, you might have heard this word El Nino, La Nina, perhaps in some weather reports or newspaper articles, right, which essentially talks about, the temperature gradient that exists somewhere on west of South America. And it essentially has a lot of say that whether California would be wetter or drier, whether Indian monsoons, which are essentially very important thing for India and Indian subcontinent, they would be stronger or weaker. So that's an expectation, but it is strongly tied to certain variabilities that are happening somewhere in South America, close to South America, and these kind of differences may give us warmer winter, a weaker monsoon, and so on. So that means if there is an El Nino year, my expectation has changed that this year let us expect a warmer winter. Let us expect that monsoon would be weaker. So expectation itself is not fixed in time, right? So climate is always changing, so are the expectations, and these variations also happen at much smaller scales, seasonal to intra-seasonal scales, intra-seasonal to seasonal scales, annual scales, decadal scales, and so on. So one thing we have to understand is that that lot of components, even at small scale, are changing, and that is part of the natural variability of the system, and lot of effort, scientific endeavors go in distinguishing what is this climate change versus climate variability. right? So not every single extreme that is happening is climate change, or of course a lot of details need to go there, but climate variability and change, they are always present in whatever climate related phenomena we are going to talk about. Now let's go a bit back, let's not talk about today's expectations or what El Nino or La Nina will bring. Let's talk about Cretaceous period. So now geologists have strong evidence. Of course, a lot of research goes into looking into ice cores and of course that dating back various aspects of carbon stored, deposited in those ice cores. But there is a strong evidence that millions of years ago, Earth was even warmer on an average than what we have today. And life was thriving. So if average temperature of Earth today is 15 degrees Celsius, temperature at that time would have been closer to 22 to 23 degrees Celsius with all uncertainties, and life was thriving. If not humans, right, we had rich diversity of flora and fauna, then what's the problem? If life can thrive there, if we go 1 degree Celsius, 2 degrees Celsius, 3 degrees Celsius warmer, what's the big deal? That time it thrived, again it can thrive, right? Then let's look into pointer 2, which is not as old as million years old, but a few thousand years old. Around 25,000 years ago, there was a period called as Ice Age. And Ice Ages, it was the last Ice Age from 100,000 years, 25,000 years, with all uncertainties, plus minus 5,000 years, because these are based on the paleoclimatic reconstructions that geologists often do and get that information to us, and different ways to design experiments gives all sorts of uncertainty, but still there is a high confidence that was the period when we are under Ice Age. That time no humans came into picture, no industries were there, still we were pushed out of Ice Age. So average temperature that time was 8 degrees Celsius, around 46 Fahrenheit. And now we have 15 degrees Celsius. Even if we go to pre-industrial era, we may be talking about 15 degrees Celsius. So what changed that 8 degrees Celsius to 15 degrees Celsius? There was no human-induced GHG emission. Still we saw an increase from 8 to 15 that pushed into our this relatively warmer period, which again would be followed by an ice age with all estimates of geologists, earth scientists, and so on.
So in terms of, please interact. I mean, don't just be listening mode. There are a lot of things here he's saying, which, as Danish also said, will become clearer as you interact. So please feel free to, stop.
Parts per million to 280 parts per million. Right? So carbon dioxide in atmosphere is typically measured in gigatons and then converted into the concentration, which is think of it as milligram per liter. If you take a cup of water, put some salt, keep on adding more and more salt, C has higher concentration because milligram per liter of saline content is higher in comparison to fresh water or water in the pond or a lake. So that's a similar analogy that we use here. There was a change of 100 ppm from ice age till modern pre-industrial world. From modern pre-industrial world till today, we have only added 120 ppm. We added 100 ppm that time, 120 ppm on an average, change was 110 ppm that time, 110 parts per million now. Then why are we so worried? We have changed the amount of carbon dioxide from ice age till pre-industrial era by same time, by almost same amount. From pre-industry we have done it now by almost same amount, no humans involved. Strong evidence that human induced activities have brought us here, and that's why we have been talking about it in all possibilities. Then let us think about it in a bit different manner. That is, let us go back to ice age and set up our industrial era around that time, and we will try to push out Earth out of ice age. Not through natural processes. It took us some 25,000 years to go from ice age to pre-industrial state without humans in 15,000 years. Now if we go back to ice age, hypothetically industrialize the world, put a lot of industries, carbon emitting sources, what do you think how much time it would take for us to go from ice age to the other side? It took 15,000 years naturally, 20,000 years naturally. What would be the answer to this green box?
100 years.
100 years. Any other guess here?
500.
500. So, in fact, answers are with that uncertainty. That 100 to 500, average around 250 years, because we are only reconstructing past Earth. We don't have actual data on how much ice was exactly there, but estimates are around that with all possibilities, 100 to 500 years. And believe me, this is a very narrow uncertainty bound for an Earth scientist or somebody working at geological timescales. 100 and 500 years would be a dot. Right? Because it's in comparison to 15,000, 1 million years and so on. So that's the spectrum at which time scales change, and that is the worry. That is, it took us around 25,000 years without humans to add that 110 ppm. And with humans, we would have accelerated that process by 200 years. Then again, what is the problem? Because life thrived even with warmer temperatures, so we can still thrive with warmer temperatures. Why are we worried?
Life can't adapt.
Life can't adapt at this particular rate at which we are inducing that particular change, and that is precisely the worry that why we should be worried about climate change, because issue is not whether some particular temperature regime is optimal or suboptimal, right? The point here is that if changes are too fast, then gradual, right? Ecosystems, not only humans, but the flora and the fauna and species with whom we share this particular planet, they would not be able to adapt, if not all, but many of these would not be able to adapt to these particular changes. That is why when we talk about climate change, right, we talk about warming world, we also try to see that is there any gain for certain species when Earth is warming, and answer is yes, right, because in Himalayas, for example, you have longer growing seasons now because the warmer days have increased. So there is always a positive and negative relationships that we talk about in a warming world, because for certain species it may be sort of a blessing, for certain species it is going to be a bane, and there is always a balance, but majority of the species, including human beings, including various crops, are not going to adapt at that particular rate at which we estimate that things have changed and are going to change. Now, we understood all of this, then why we talk about modeling, it will become clearer as I talk about. But unless we want to take some action, if we want to have an informed decision making, and if we don't know about the system, we are only going to make guesses that are going to be far, far away from reality. It's just, if we don't know enough about the system, and we want to do something about that, it's like buying a lottery ticket and thinking that, I am going to hit the jackpot and I am going to be rich, but we know that chances of that happening is 1 in million or 1 in few millions and so on, right? So it is not worth it that we just sort of, without understanding the system, start talking about it, start making policies about it, start doing detection and attribution of specific events, because there are costs on either side. For example, if we say, every single extreme event that is happening should be attributed to climate change, let us prepare for everything, we are at risk of over adaptation. with limited resources, right? High level of inequality across countries, within countries, we are at higher risk of over-adaptation. On the other hand, if we say, change is part of the system, let's not do anything, and there is actually a fundamental change in the processes that are shaping our Earth system, we are at risk of under-adaptation, and we are not going to adapt where it is needed the most, and that's where understanding this system, be it for engineer, scientist, policymaker, becomes important at some level, that there are uncertainties involved, and what are the sources of that particular uncertainty. That becomes very, very important for us to see from a unifying lens, that it doesn't matter. If I'm a policymaker, I need to have at least some rationale that what is the science behind that. Even if I'm an engineer, I need to understand what information I have to pass on to policymaker so that decisions can be taken, and that is exactly why we need to have at least some bird eye view of Earth system, that what goes inside that. As I said, lot of processes happening. What we see here is close to Earth's surface. Sun is the source of energy, giving us energy in form of short wave radiations, and Earth basically reacts to that. Temperature increases. Once it gets hotter, it emits radiations outwards. We receive everything as short waves. Everything is emitted or most of it is emitted as long waves. When it is coming down, it will encounter clouds, it will have aerosols, some of it may also get reflected, scattered back, and then we try to write maths equations for these processes to really reach to an answer to the questions like what is the average temperature of the Earth when all these processes are happening. What would happen if one process is changed, or it changes in fundamental nature, if the concentration increases, decreases, and so on. And when we talk about Earth system processes, lot of action happens in first 10 kilometers or so, or first 30,000 feet or so, right? Because by virtue of gravity, lot of atmospheric mass is concentrated in first few kilometers, right? And typically at 10 to 11 kilometers we have stratification in various layers of atmosphere. So for today we are going to focus on this particular area, and we are going to simplify a lot of processes. For example, here you see clouds, here you see different types of clouds. It is important for them to have here, but for a first lecture it is not as important to include them into our modeling process and so on. So, and as we keep on going up, the pressure reduces drastically, and that is one typical reason that the cruising altitude is just above 10 kilometers, so that there is least amount of drags and pressure forces that are felt at that particular level, right? So even such a simple understanding of vertical structure of atmosphere tells us at what altitude hundred thousands of planes should fly. Now think about it. If we understand more and more about these systems, how many mysteries we can reveal about this fascinating complex system. Now interestingly, if we apply similar philosophies, similar mathematical principles to other planets, answers would have been much more simpler, right? That is because there is no atmosphere for many of the systems, there is no life on many of the planets that are in our neighborhood. But they also serve as our validation ground, because Earth becomes too complex of a system, right? When our missions go to Mars, when they go to Moon, they also bring us that highly valuable data, that how our simple models will perform for those systems which are relatively simpler than what we have here in terms of their atmospheric composition, or complex when we go to satellites of the giant planets, right? So that is where all things make sense when we try to see it from a unifying lens of climate, that what is that. Now, as I said, atmosphere is going to be our major element of discussion in today's lecture. So before we make comments about atmosphere and changes in composition, let us look into what essentially constitutes, and this is from high school geography class book, that there is nitrogen, majority of it is nitrogen, relatively inert, peacefully staying there, right? Very important for our plants. Plants absorb them, give part of it back. So relatively inert gas, right? And staying there. Same with oxygen, around 21% goes there. The entire action is happening in rest of the pie chart. This is where most of the concern is. Same with argon, relatively inert, still leaves us with fraction of gases that we are going to deal with. Here you will see water vapor, methane, hydrogen, ozone, xenon, carbon dioxide. Just look into the percentage of carbon dioxide in Earth's atmosphere, 0.04%. And I'm sure since this dialogue has started and whenever program assistants have been talking about lectures and you might have been also hearing various people, every discussion is around carbon footprint, agricultural carbon footprint, my flight's carbon footprint. What makes it so prominent? Why we are not talking about my water vapor footprint? And I think that was the reason I was made to read a lot about what is happening, right? Because as an engineer, we will get data, we will do the analysis, prepare beautiful figures, write papers, but still it's important to understand what is behind the scene, from where I am getting data, why this particular concept is emphasized. Before I go to the answer, any reason why we are only talking about carbon dioxide and not water vapor? Water vapors actually has much more greenhouse potential than carbon dioxide, by the way. So for example, when we go for sauna bath, right, we feel that how hot it is in comparison to outside. That's a classic greenhouse gas effect, right? So why we are so obsessed with carbon dioxide? Any answer? Again, idea is to have a discussion. Don't worry about right answers or wrong answers. Right. We will try to get towards accuracy part as we go ahead. But why you think yes, please?
I feel like we haven't really altered the emission of water vapor into the atmosphere, whereas we have altered the emission of carbon dioxide. So we're seeing that our emissions are causing this possible climate change, and we're seeing that we have altered carbon dioxide. That should be our focus.
Okay, very good reasoning. Yes, please.
Carbon dioxide stays in the atmosphere for longer, so that's
Okay. So, like when we talk about longer, any initial estimates for how long are we talking about? Like in terms of time,
Yeah, time frame, like 100 to 1,000 for carbon dioxide.
years or
Years.
days? Okay. And what do you think would be estimate for methane and for water?
I don't know, maybe lower hundreds.
Lower hundreds. Okay. I'll come to answer as we progress, but these both points are very valid points. And since it's a coupled process, perhaps water vapor quantity might have changed or not changed, right? But answer would be certainly around the something called as resident time. Now, interestingly, oxygen, nitrogen, more or less it has been constant. We have satellites monitoring. We have vertical balloons that keep on going back and forth from various observatories, which centered around hypotheses that this particular gas has changed in composition or not, and there is a strong evidence that the variations in N2 and O2 are minuscule or very different, very difficult to be differentiated statistically from their pre-industrial level. I am again and again coming back to sun, because that is going to be our center point of our zero-dimensional models, right? So sun has been there for billions of years ago. It is going to be with us for as many years it has been in the past, right? It is a constant, more or less constant source of energy, right? Earth keeps on changing, may tilt, may increase the tilt. There may be some cyclones happening at surface of sun. They may change the amount of energy we will receive there. But again, the variations are minimal when we compare it to the other processes that essentially take the center place in this climate change discussions. So we receive on an average 1362 watt. W is the letter. That I'll write it when time will come, but 1360 watt per meter square. Just to put it in perspective, this projector lamp is somewhere of 100 watt. So if I hold a sheet of 1 meter square in front of that particular projector, I will say that this sheet is receiving 1 watt per meter square of energy from this projector. I am talking about 1362 watt per meter square in outside atmosphere. So if I go maybe 300 kilometers away from Earth's surface, put some device, a sensor on a satellite, I can really quantify this 1362 watt per meter square, and there are many observatories that now we have been able to establish through our satellite networks that also measure how much of this irradiance is changing in outer atmosphere. But the good, very strong, high confident estimate is 1365 watt per meter square, and I average between that 1362 watt per meter square. So 1300 projectors put on a 1 square meter of piece of paper, just to put it in context. Okay, and it's a lot of energy that is coming from sun on that 1 meter square. So far so good. I hope I have not lost you. I know there are a lot of technical details here, but let's try to hear it as a story than the math or science, because once we have a story, we can always add numbers back. Now what happens is that we will worry about this side later. As I said, temperature of sun is, any guess what is surface temperature of sun? 3 million? That's too hot. Any idea? Yes, please.
Like 9,000 Fahrenheit?
So 6,000 degrees Celsius, right? And perhaps on some of those solar cyclone days it could reach up to 9,000 degrees Celsius, which of course, see the uncertainties. I think the point here is uncertainties. That's where I'm saying whatever answer you are saying is going to be in the range, right? So please speak up. So 6,500 degrees Celsius and adding 273 would not make any difference here. So around that much of Kelvin is the average temperature of the sun. Now whenever bodies of that temperature, there are certain laws in physics. We need not worry about the name of the laws, but there are laws that relate that if body is at certain temperature, what is going to be the frequency or wavelength of that particular radiation that we are receiving. The name is Wien's law, but again, let's not worry about the name of the law, but that gives us not high confidence, it's absolutely dotted confidence that energy that we receive from sun is in form of short waves. These are high frequency waves that are coming to us, right? Because temperature is high, the energy of emitting source is very high, so the waves that originate have very high frequency, right? They keep on oscillating very fast and reach us. Now we have, if this atmosphere would not have been here, we would not be having life, as simple as that. Right, because 6,000 degrees Celsius directly getting exposed to, as far as we know so far, there is no evidence of life that can sustain that particular temperature, including microorganisms. Again, that may change as explorations happen. I'm not going there, but in our known solar system, there is no evidence of life at that temperature. Well taken, and that's where atmosphere acts as a buffer. It reduces 6,000 degrees Celsius to 15 degrees Celsius. 6,000 degrees Celsius to 15 degrees Celsius just by virtue of something that is present over depth of 10 kilometers, 6 miles, something around that. And that's where this fascination is, to understand more and more about this. Now, interestingly, not everything reaches us. A lot of that is bounced back by the atmosphere in upper layer. At 30,000 feet, even above, atmosphere will say some 14-15% radiation can go back, right? Then we have water on the earth. When we have water and source of energy, water evaporates. When water evaporates, it becomes clouds, right? Clouds are pulled down by gravity, stay up by their buoyancy, and they keep on floating at some equilibrium where both these forces are matched. These clouds also say, okay, we will also reflect some of it back. We will also absorb some of it back. We will absorb some of it, we will reflect some of it back. Then we also have aerosols, right? We also have gases like ozone in outer atmosphere. So ozone is one of that particular gases that is outside that 10 kilometers zone. And it also reflects a very small percentage, 3 to 4% of all the incoming radiations back. But ozone, aerosols, clouds and atmosphere, right, the gases of various gases do the job for us to keep us largely insulated from this. Still, 70% of radiations reach to us. 30% are reflected back. 70% reaches us. Right? What is 70% of 1300? Any idea? You can use computers, calculators, cell phones, just give me a number. 900 something, 900 watt per meter square. Still 900 watt per meter square reaches us starting from the sun. That is still scary enough to increase temperatures to a few thousand degrees Celsius. What is happening now? So atmosphere, good confidence, 30% is reflected back, 70% comes to us. Right? This 70% is certainly coming to us. What is happening with that? Why we are not in 1000 degrees Celsius? Because I said it's watt per meter square. Had Earth been a one-dimensional object facing the sun, that would have been a problem. But we are oval in shape with an incline. So we only get a pi r square, a circle that is exposed to that. Right? So the effective radiations that we receive from the sun get reduced by 1/4, because area of a sphere is 4 pi r square, area of circle is pi r square. So for the same dimension of a ball and its projection, we are looking at surface area of 1/4, if I put it in simpler language. Right? We did not worry too much about mathematics. The ball and its shadow, they would have 1/4 of surface areas when you are talking about same radius object with sun at 12 noon. Okay? So 1/4. So what is 1/4 of 1300? Around 400 something, right? You see this number? 341. Very close to 1/4 of 1300 is what effectively matters for us in a given area. Even now, there is a bit cloudy outside, but if we find a way to go above clouds, right? I mean, even at 30,000 feet, where our aircrafts fly, the solar insolence that we will receive is going to be in range of 250 to 280 watt per meter square. And all modern flights are equipped to keep track of that, keep a record of that, because they are there now, right? Temperature, pressure, etc. They are continuously monitored. So that's a very reasonable estimate that we are looking at, 340 watt per meter square, by virtue of our shape, by virtue of our distance, by virtue of what is reaching to us because from the sun. And you know, all these yellow so far is short wave, high frequency, high energy waves coming to us. Some of them get reflected back by the clouds. Some of them are able to penetrate through them by virtue of the energy that they have. they are also able to, unfortunately or fortunately, we'll talk about that later, go through greenhouse gases. Greenhouse gases cannot stop short wave radiation. Right? Given their chemical structure or chemical, the way the various atoms are arranged, they cannot stop the short wave radiation and they are able to get in. Right? Even extreme on other side is bad. If they would have been able to stop, we would not be having temperatures of 15 degrees Celsius, we would be somewhere in minus 10, 15, 20 degrees Celsius, which again also is worrisome. Right? Even lower. We can easily do the math after today's lecture about that, but we get, after everything happening, some of them being thrown back by clouds, some of them going back from the aerosol, some of them get absorbed by the atmosphere. Atmosphere absorbs it, increases its temperature, right? Around 161 reaches the earth finally. We get 161 watt per meter square. Started from 1300, around 10% reach us from the surface.
Is there a gas that does like obstruct short wave radiation?
Yes, ozone is one.
Oh,
That's why when people started talking about ozone hole, right? It was a serious matter of concern exactly because of that. Right? Ozone would not let majority of these short waves getting through that. Right? Or at least would bounce back significantly more than these greenhouse gases can. And of course there are other gases, but again if you see, again go back to that pie chart where composition is so minuscule. Right? It's always that how much quantity is also present. That's why ozone gains prominence, but I'm pretty sure that there are other trace gases which also do exactly similar what ozone does to us, but again they're presented in minuscule quantities. So far so good. I hope I have not lost you at this point. So yellow 161, this 161 is crucial to us because what it will do, it will increase temperature of the earth's surface. This would be absorbed, right? It will start evaporating water from here. It will increase the temperature. It may be used as a sensible heat when it increases the temperature. It may be used as a latent heat when it just evaporates water from liquid to gas and so on. Now interestingly, process does not stop here. Earth absorbs energy, achieves a temperature, and what happens when any object is at temperature above absolute zero? It will emit. It will emit, right? That's why when we start heating an iron piece, it becomes red. What it is doing? It is emitting, right? Light or a wave of that particular frequency that appears as red to our eyes, right? So again, science has always been fascinating for centuries. People started studying that, and there was a very famous law that was coined. Again, let's not worry about the name, just hear it. Stephen Boltzmann law was coined that basically relates that a particular body at whatever temperature, how much energy it will emit, right? And these emissions are not in short waves, these are long wave radiations. We received as short waves, increased temperature of Earth's surface and started emitting as long waves. Now if these greenhouse gases are there, right, what the problem is that they cannot resist the short waves to go through, and they do not let long waves to go through. Right? Given their chemical structure, short waves can go through, long waves cannot go out. And they absorb this, increase their temperature, and again start radiating energy in all the directions, upside and downside. So it becomes sort of a ball going between the walls that is thrown between that. Some energy goes hits back, hits back, hits back, hits back. This is precisely what we call as greenhouse effect. Something came in, cannot escape. That's why your cars are warmer when you put them outside, right? Because short waves can get into through the glass shield, right? But they would not let the long waves escape. That's why temperature inside car is how much degrees Celsius typically it's warmer? Just by your sort of perception of temperature, 3 to 4 degrees Celsius, would it be a wrong guess? I don't know, I mean I'm just recalling from experience. It certainly feels that if outside is, please also if degree Celsius to degree Fahrenheit, if I am more comfortable in degree Celsius, right? But we are here more interested in the change, percentage change, so units would not matter. But 3 to 4 degrees Celsius warmer, just because of that particular car analogy that I gave. Same thing happens with atmosphere. We trap heat, increase temperature, and we do not let this happen. And if you see here, what is happening? 356 is going, only 40 is able to escape, 90% stays back, 333 comes back. 333 comes back, 396 goes back, and this cycle essentially becomes a part of long wave cycle in our Earth's atmosphere. You have, many of you might have seen these kind of plots in your geography classes, right, in school. What changes from here to here are the numbers, right? We use observations, we use experience of observing various processes just to get this number. And this is not a trivial exercise at all. Putting each number is worth billions of dollars of investment, because you need monitoring stations, you need sensors, you need long-term continuous monitoring that you are not measuring an anomaly but an average behavior or long-term behavior. So this is not a small step by any means to quantify that, right? In fact, there are a lot of uncertainties around this number. Somebody would say it is 161, some other research group would say no, it's not 161, it's 200. Some other would say no, it's not 200, it's 140. So it's always some uncertainty that we are dealing with. What is important is that 1360K, around 10% is being used to heat up the earth, and carbon dioxide is trapping that, and that is essentially governing all these particular discussion. And so far we simplified it a lot, but we also keep on making these observations vertically, horizontally, along the equator, across the equator, and so on, to get a full picture that what is happening at individual scales. For example, if we see that what is happening at the equator, we are receiving around 400 watts per meter square because of our shape. You go on either side of the equator, this would come out to be around 300 and eventually decreasing to somewhere to 80, 87 watt per meter square when we go to poles. That's why the average number comes around to be something around 250 to 370 and so on. But because we are talking about average behavior. Similarly, if we are receiving more, we are absorbing more. Right? That's why peak of absorption happens around the equator, and it keeps on decreasing here. And if you see here, what is happening at poles, they are reflecting more than what they are absorbing. Equator is absorbing more than it is reflecting. So if a particular location gets more than it gives back, what should happen to its temperature? It should increase. If you are taking more radiation than you are sending back, your temperature should increase. Absolutely. And vice versa. So that means that poles should continue to get cooler and cooler, and equator should continue to get warmer and warmer. Every day there should be a change. Is that really happening? Do we see that 1 degree Celsius change every 5 years in equator, or 1 degree Celsius on negative side on the poles? No. Any reason why not? What we have based in this discussion so far? So you are absolutely right in your reasoning so far, that it is absorbing more, giving less back. It is taking in more, sending back, so its temperature should increase, opposite on other side. But in reality, yes, there are variations in temperature, but it's not like 1 degree Celsius per year, or 10 degrees Celsius per 10 years, or some high number. But this is absolutely correct. Even if you look into outgoing radiations versus incoming radiations, this is at what is happening at poles, this is what is happening at equator, and this should increase. But why not? Who is helping us maintain this quasi-equilibrium? Huh? Plants, okay. They are actually big role contributors to that. What else?
Ocean.
Oceans. Right, that's where I said it's a coupled system. We started from sun, we talked about earth, we talked about atmosphere. Oceans got upset, why you are leaving us behind? We would ensure that there is a quasi-equilibrium. I am not saying equilibrium, I am saying quasi. Quasi means false equilibrium, not a true equilibrium. Right, quasi-equilibrium, plus minus variation would always be there. But now it becomes two entities at different temperature connected by a fluid that can flow. Right? It flows, and when car gets heated, what we do? Radiators are there to bring temperature back by virtue of moving a liquid. That's exactly what oceans do. Oceans are radiator of our Earth's surface. They would ensure that the thermostat of Earth does not cross down erratically beyond certain range, what our radiators in motor vehicles do. And that's exactly the similar role that, water flows, waves form because of this differential heating. Because of this, we get winds coming into picture. Winds produce wave. When all these motions happen, this energy eventually gets balanced out, right? And this is essentially where life gets fairly interesting when we talk about Earth system. So now things are so systematic. We have sun, we have beautiful plots going linearly from X to Y. Everything is sorted out. We also blamed oceans or credited oceans. And it's easy to visualize. Sun has been constant source of energy. Then what has changed in last so many years? Let us talk about that. Sun has not changed, right? I mean 1300 is a good number. Earth has not changed in its shape. In last 200 years at least, the shifts in axis or its position, location has been minimal, right? There are observations for that, right? What has changed? So if you look into carbon dioxide concentration, this is at Mauna Loa Observatory. This is quoted, cited, referred to almost in all scientific studies, including IPCC WG1, the physical science basis reports, that how carbon dioxide concentration has changed. Yeah.
Udit, can you tell us how much carbon dioxide concentration varies across the world? What we care about in terms of greenhouse carbon dioxide concentration? And why one observation in Mauna Loa or one observation in a glacier ice sheet, right, whether it's for recent or for past, why we at least value that as opposed to saying this is just one observation. So for example, many of you may have heard of rain gauges. If I take one observation of rain gauge in one place, Bangkok, let's say, in that temple that we visited, that may change just from that temple to here in our hotel. Right? Significant. And we know that. So even there we have to measure at so many points. But here is saying, okay, somewhere in Hawaii, we'd all love to visit Hawaii by the way. But somewhere in Hawaii there is this one place where we take this concentration and we somehow treat it as somewhat representative maybe Similarly, glaciers, somewhere in the Arctic or somewhere, you look at paleo, glaciers, radiocarbon date, they open these glaciers and see the composition of the atmosphere and say, okay, we treat it as somewhat representative. So why is that and how is that? And I was just blabbering to give you some time to say.
Yeah. Thanks, Arup, that you asked this question today. If you would have asked this to me at time of qualifier, I would not have been standing here. Right?
I will talk
I will not-
the committee
I will not have a PhD that time because I didn't know it that time. But today I am prepared because I read about it. Right? So when I showed that plot, composition of atmosphere, right? The atmosphere is in well mixed state. You take observation at multiple points away from a particular source of that particular emission. So for example, if you are very close to one particular industry and you just go vertically up and measure the composition, you will see there are going to be variations in N's and O's and various other gases. But these laboratories, they are somewhere away from the point or line sources of these emissions. So one would be in Mauna Loa, for example. One of the dialogues actually visited Amazonia, and I was TA at that time. And we also observed, we went to the forest observatory there, right, in no man's land, a vertical tower going all the way above Amazon forest to make certain observation about vertical and horizontal fluxes, and they call it as a flux tower. Right? And atmosphere is indeed in well mixed state because it's in constant motion because of the winds that are flowing throughout. We have jet streams, we have trade winds at different levels, we have westerlies, we have easterlies, so it is always being stirred continuously thanks to sun. Right? So whatever observation you are making at Mauna Loa, it's a good representation. There are going to be variations, but not as significant that there you would have a concentration of 400 ppm and here you would end up with concentration of 200 ppm. So variations would be of 405 ppm to 390 ppm to 380 ppm depending upon the local dispersion characteristics. So this well mixed word becomes an important, and hence observatories at strategically located location away from point sources are reliable measures. Arup, would I pass?
I have to talk retrospectively to your PhD committee.
Yes, sir.
Oh, wait a second.
Even some of the climate change critics have raised this concern of this is just a one data point. But then eventually the people start gauging it over different oceans, and what they observe is that the results are similar across the world. So that's how we usually represent one representation rather than the whole world.
So also, like, there is always signal is to noise, right? So this signal ratio, and there are studies that talk about signal is to noise ratio in all these observations. So here we are essentially talking about the pattern that despite all the noise, what is a clear discernible trend or pattern we are able to observe. Also I started, right, somewhere around 280 ppm, right, from 1885 till 1900s. We didn't change drastically, but see what has happened after that. With all the diurnal variations, in 2020 we are looking close to 400 ppm, 400 parts per million. In last 15,000 years, from Ice Age till pre-industrial era, we went from 180 to 280. From 1950 onwards, we went from 320 to 410 ppm, and that rate of change is dramatically higher than what would have, yes.
Might be overlooking something that isn't like Hawaii relative to the equatorial, and since then, like, why is there seasonal changes? Like, aren't there there are seasons at the equator?
So, because it's not just the physical processes, right? There are also chemical deposition of carbon dioxide in different forms that is happening, which has strong functionalities with the meteorological state. That's why these variations come into picture. right? Because when we talk about carbon dioxide or any other gas, for example nitrous oxide, right, they keep on changing their forms from one molecular form to another. So when we are talking about atmospheric CO2, the same rationale goes behind these particular variations. And that's why they have a strong seasonal component along with the trend. So now next question should arise. This could be all natural, right? There might be volcanic eruptions happening. This might be going from ocean to the atmosphere. How we can really say that this is anthropogenic? The sources are primarily anthropogenic, right? Because carbon dioxide concentration increased from 180 to 280 without humans. Now it could also increase from 280 to 400. So we should raise a question. We should be skeptic about this. And that's where radioisotopic experiments come into picture, where they look into that what is the ratio of isotopic mass that would come from natural sources of carbon versus coals and fossil fuels and so on. And they define it in terms of something called as carbon 13 to carbon 12 ratio. So if this ratio is on lower side, that means that the contribution of 12 that is typically found in fossil fuel is on higher side, 13 is typically found in the natural sources of carbon, and 12 is typically found in the fossil origin carbon and so on. And there is a significant decline in organic matter derived sources, and again there are lot of experiments, lot of studies that keep on happening even now as I am talking about it to really keep on refining these estimates, but by and large there is an understanding that this 400 ppm, the relative contribution of natural sources is dipping and anthropogenic sources are on increase, and hence by and large that there is a very strong evidence that this change is primarily because of fossil fuels burning and going into atmosphere and becoming part of these greenhouse gases and so on. Going back to this composition, well mixed atmosphere would look like this, but we will have water vapors on top, carbon dioxide, methane, nitrous oxide, industrial gases, and all of these greenhouse gases, but most of the discussions focus around carbon dioxide because of their residence time in the atmosphere. So a drop of water vapor stays only for 8 days. 8 days. So it comes here, evaporates, comes back, evaporates, come back. The average time is around 8 days. When we talk about carbon dioxide, there are variations dependent on temperature and other meteorological states. It does come back, but after 300 to 400 years. And this is averaged over a long period of time. That is, what is the residence time? Think about it. We take one molecule and keep on tracing for on an average for how long it will stay in that particular state. With water vapors, it totally makes sense that today it's in ocean, it will evaporate, become part of the cloud will condense, and we will get the rainfall in form precipitation in form of the rainfall or snow or whatever. Right? So we can keep on saying, okay, this is going in circle. If we find a way, a mathematical way that hydrologists do to average out for each and every molecule, the number comes out to be 8 days. For carbon dioxide, it is in few years, 5 to 200 years. Methane would be 10 years. Nitrous oxide is also very high. Carbon dioxide, that's why if you see lot of discussion in agriculture sector are also focused on nitrous oxide. Right? That what is the useful and non-useful form of nitrogen, how much of fertilizer should be applied to minimize the greenhouse gases coming from nitrous oxide in agricultural sector. Right? So it's and at the end we need a unifying language to really understand the implication, and we try to convert everything in terms of carbon dioxide equivalent emissions based on the chemical characteristics of carbon dioxide. And we end up saying that 77% of 2000 emissions that contribute towards greenhouse gases are primarily in form of the carbon dioxide. Now, carbon dioxide is something we observed. Carbon dioxide is not temperature, it is not precipitation. still we are far away from reaching any conclusion. Then we also started measuring temperature. Right? We can measure temperature, we can put thermometers everywhere at different places, and temperature is not a well mixed variable. There is going to be, because of different amount of energy, different land and water ratios that we have in north hemisphere, south hemisphere, different form of circulations happening, we are going to have these large variations in these temperature fields. So what we observe here is that from 1880, average temperature around 13.8 degrees Celsius, we are going somewhere around 15 degrees Celsius, and this is the number from where I started. Average temperature of the Earth's surface is around 15 degrees Celsius. Right? We are still colder than the millions of years ago period, Jurassic period I was talking to, about around 22 degrees Celsius. Right? But again, the rate of change is something that we have been talking about. So there is a trend going upwards, but similarly we can measure various levels. Now we have satellites, now we have gauges, now we have amazing instrumentation facilities that we have developed, right? Both at micro scale and macro scale, as I mentioned, right? There are so many planes that take off vertically, and they are equipped with hundreds of sensors. They can really give data at near real time at different locations, given they are equipped with that, and based on that we actually get variation that at some level it is increasing, at some level it is decreasing, because ultimately it's a thermodynamical system. If there is increase in one part, there is going to be decrease in another part, so that things are more or less in equilibrium. It's not like everything is global warming would mean that all atmosphere levels are going to get warmer or otherwise and so on. Right? So there is variation that we are observing, and despite all the variations, there is a discernible trend that we see. Similarly in Arctic ice, similarly in glacial fields or ice fields that have been retracting, evidence coming from on-site satellite observatories. I will not go too much into causality, but point here is to show that that changes are there, but this is more important to tell, because you have been talking about changes in temperature, snow ice, the Arctic ice is melting, and this is the precipitation is decreasing or increasing, drought is changing, and so on, right? But most important question is, we started from carbon dioxide, which is a gas. We are talking about water vapors, we are talking about temperatures. What is the relation? What is the physical science basis? What if this increase in carbon dioxide and increase in temperature, it is mere correlation than causation? Right? One example is that I live in India. One of the cities there is Ahmedabad, a fairly large city, right? House to 7.5 million people. As I am growing, as my age is increasing, number of cars in Ahmedabad are increasing, right? And correlation would be close to 0.9 or something. So if you plot number of cars versus number of my age, it is going to go up, right? Am I causing increase in number of cars in Ahmedabad? Right? I can buy one or two, right? But that particular rate change, it is mere correlation than causation. Same thing can happen here. On one axis I can plot carbon dioxide, on another axis I can plot temperature. Both of them may increase simultaneously, and I can say that this is just correlation. It has nothing to do with temperature, it has nothing to do with precipitation and so on. Right? Just by looking at data, I cannot be convinced thoroughly that indeed this is a problem. Right? And as I said, if things are so systematic, easy to visualize, and sun has been constant source of energy, and we have quantified to great extent what has changed, why there is so much uncertainty around aspects of climate change? We understood everything today. We talked about sun, we said long wave, short wave. Physicists in the house are convinced that yes, short wave is right, long wave is right. Then why we have so much uncertainty? Yeah.
Is it because like we sort of like elucidated the individual mechanisms, but the atmosphere itself is like so dynamic and complex?
Absolutely. Absolutely. That we understand a lot about Earth system processes. There is still a lot that we don't understand. Right? And in fact, in climate, we often say that, right? The most crucial pieces of information are still missing. Right? And a lot of efforts keep on happening around that, AMIPS, AOMIPS, CMIPS, which essentially endeavor to improve understanding of these processes year by year, decade by decade, to include more detailed representation. Because we have to understand that Earth is a giant planetary scale heat engine that is in motion for millions of years, continue to stay like that, churning the oceans around, producing winds which are far, far more complex that we can just talk about qualitatively and understand everything about it. It indeed is highly complex system that has so many components. For example, this is again a very, very simplified view of the typical average patterns of winds that flow on this particular Earth. We are talking about everything so far with a great sense of determinism. We know this, we know this, we know this, Earth is warmer. But there is a lot of randomness associated in these particular processes that sometimes we don't even understand, or they are inherently part of this particular system. Yeah.
Like, I'm just wondering if there's a way to like, is there a potential that the Earth is changing faster than science allowing us to understand the Earth and its systems? And so it's like just a futile endeavor to try to understand some dynamic system.
In some cases, I mean, of course, certain processes evolve at much faster scale, right? That the processes may be changing faster, but and always it's like it's a chase going between the science and the understanding, and to larger extent from 1850 you see the rate change, how things have changed. But I think most, Arup may correct me if I'm wrong, that the most serious inquiries quantitatively in this climate modeling started gaining prominence around 1950s, 1960s mathematically.
Yeah.
So processes were much faster from 1885 till 1950, and then we tried to caught up starting from 1960s, and it does not progress linearly. So it may be a jump and then a long period of using that understanding what we achieve, either remain with that as a status quo and then go to next level of technology and so on. So in some sense, yes, I mean processes are evolving at faster rate. Then we started even thinking about them. When they gained our prominence or attention, and how easy to resolve, separate them out, because there are so many sort of gears, right? As I said, we understood so many things, and then I just threw one phrase, is it correlation?
Climate modeling and understanding climate science. I mean, there are so many aspects to that, but so many aspects to climate in general. But if you're focusing on modeling and the science, progress has been almost in tandem with high performance computing, including data, because these things take a lot of time to run, some of these processes, such as cloud physics and things like that. So and computational sciences, methods, hardware, software in general has progressed very fast over the years. And climate is one of those domains, climate, weather, etc., that has used up almost all of those resources and says now we need more. So the progress in our understanding of the science and high performance computing, data science, etc. has tried to keep pace with each other. Given all that, I would say progress in the core scientific understanding, basic scientific understanding is always a bit slower than progress in, let's say, compute speed, hardware, etc. And definitely the stakeholder needs have progressed much beyond, much faster than any of these, or at least in terms of climate science itself, right? The needs have grown very fast. So there is that. The other thing is, just as an example that we still don't understand everything, cloud physics is a major gap, remains a major gap. Even last, the last IPCC scale projections from what are called Earth system models. They used to be called global climate models, now they are called Earth system models because they include so many components of the Earth systems. So some of those models included what we as in collective we, the community thought is an improvement in terms of cloud physics and got huge runaway warming. And then on subsequent analysis, people thought, no, we shouldn't include that yet because it's not validated and it will, it will scare everybody too much, even more than the standard things. And you have to be careful about those things, right? If it's changing that much, you have to validate again and again. So the IPCC said, let's wait. And as of now, the consensus is emerging that no, maybe that runaway warming is not what we expect. Maybe those cloud physics parameterizations work well in a weather context, but maybe not so much in a climate context. So that's just one example where it clearly shows that yes, the science, we do not understand everything about the science. There is a lot of uncertainty, a lot of variability, a lot of things, a lot of knowledge gaps and internal variability in our understanding. The point is, despite all of that, there are some signals and there are some things we know that needs to be done, which then needs to be taken up by planners, decision makers, economists, biologists, social scientists. What do these mean? Engineers, what do these mean, and what action we can take with that, and where we have to be here. A lot of uncertainties. These uncertainties are genuine. You cannot wish them. The issue is that typically these are not the same uncertainties that denialists talk about. They'll say, we don't understand anything about the science. You have all these things. Carbon dioxide is not an indicator. Carbon dioxide is all kinds of stuff they'll make up. One wishes that most of them, this is not all of them. Some of them do talk about certain things that are issues, and those can be good for us to generate hypotheses that we examine. But I wish that more of them would have their criticisms and base their criticisms on that part of the science and policy and economics that we really don't understand, and hopefully which we need to focus on. But there is the other side in terms of how this world works, in terms of vested interest and so on. That's different. But just focusing on this, do we have uncertainty? Absolutely. We need to work on those, yes.
So, Earth is complex, so many processes, right? And not only that, right? I mean, we receive sun, we have energy from sun, we have tilt, and then we have different land mass and ocean mass. So, a very simple question that scientists posed many years back when they were talking about materials, that if you give same amount of energy to water versus you give same amount of energy to land, which element would heat faster? So if you have to make temperature change by 1 degree Celsius or 1 Fahrenheit, do you need to give same amount of energy to water and land? What is your guess? Yes or no? No. Why?
No, because it would take large bodies of water to heat up.
But let's say that we are talking about 1 meter square, that we fix the land and we fix the area. We remove the scale effect. What you say is very important. We remove the scale effect. That scale doesn't matter. It's just 1 meter square or 1 square feet of land, 1 square feet of water. We take a source of light, let's say a torch, and put same torch for hours on them. After n number of hours, we measure temperature of both of these entities. A very simple question is, would temperature be the same or not? Simple, not essentially for us, but for people to ask who are working with material physics. And they found it no. The specific heat capacities of all entities, elements that surround us is different. Right? You might have heard this phrase that so water is excellent coolant, right? Because it takes lot of energy to increase its temperature by 1 degree Celsius and vice versa. So you can really use it as coolant. In fact, before all the synthetic coolants came into picture, radiators used to have water running through them. The reason I am bringing motor cars, radiators back into picture, because Earth is a complex thermodynamical engine, right? And that analogy actually helps us, that thermodynamical analogy do help us simplify this system to something we use, we see, we observe every day, right? So if Earth would have been an aqua planet, if it would have been all covered with water, life might not exist for us, but it would have been fairly simple to write physics for that, because now there are no different entities. Similarly, if Earth would have been terra planet, all surrounded by land, we might again, a lot of other processes would have been disrupted, no evaporation, no clouds, no rains would be existing, but still physics would have been easier. If the land mass and water mass would have been same in area, life would have been a bit simpler for scientists to understand. But we try to understand what we have, right? And we use these as baseline scenarios, that how numbers would look like if it is an aqua planet, terra planet, equiplanet, where land and oceans are in same amount. But we clearly see that there are differences. North hemisphere in comparison to southern hemisphere, north hemisphere has much more land mass than water mass in comparison to southern hemisphere. So there is a difference in temperature because of virtue of more water being present on one side and other side and so on. And what it gives rise to? It gives rise to the patterns like this. If you see here, we get more heat because of the position here. Some water goes from here, some air goes from the warmer air rises, goes back, on the way back picks up the moisture from the oceans, bring it to the equator, rises up, equator are warm and moist exactly because of this particular reason. It happens in north hemisphere, it happens in south hemisphere. This zone emerges, what we call as zone of convergence, or ITCZ, intertropical convergence zone. Lot of action happens around that. Indian monsoons happen because of shifting of ITCZ, because of differential heating of land and oceans in summers, because now it's very warm outside, right? We are in Southeast Asia, it's very warm, right? As a result of which ITCZ will shift towards here. Convergence will happen somewhere here, so you will have rainy season with lot of heat when it is not raining around that particular time. And this is essentially that governs that how these processes are going to look like. So this is essentially what we mean by this Earth as a giant engine. I will also share these slides with you. So if some button is not working because of erratic internet, it will work. But what I want to show here is that lot of energy and mass is always in transport across the surface, between the poles and subtropics and tropics, in all directions. We have jet streams at upper atmosphere, trade winds at lower atmosphere, and with mass, lot of energy keeps on. So we have agreed there is so much uncertainty, processes are too complex, right? So I used to do that when exams used to be too hard. I used to skip a lot of questions. It's too hard. What's the point in studying that or attempting that? Right? But here we are sort of mandated to answer these problems now, because problem is right here. Now we are talking about all these changes. We don't have an option not to attempt a question or answer, not as individual but as humanity, as a race. We have to understand, try to answer that, and put some objectivity to all the subjective discussions we had. But we agreed sun is interesting, source of energy, fairly constant. Earth is there, fairly constant. Atmosphere is something that is changing. Right? If we bring all the elements at same time, we are going nowhere. Right? There are so many components to take care of: oceans, land, differential heating. There are maybe 1 million terminologies associated with various aspects of climate science. But we have to start from somewhere. Right? So, but then what we should be doing? how we can, as an engineers, start dealing with these models. We start simple. We start as simple as we can get, but without violating laws of physics for that simple system. Right? We can make simple system as simple as possible. But whatever we make, we will ensure that the processes are followed. We may say no mass balance is happening, that's an assumption. But if I am talking about energy, I have to make sure that thermodynamical laws are followed. Right? And that's what gives us these generation of energy balance models. EBMs gives us MBMs, mass balance models, that we use in water resource engineering, hydrological processes to understand how rivers flow. Right? That essentially gave us GCMs, global circulation models. Right? But we will start from somewhere which is very, very simple. And one very simple model that I will make today with you, we will do calculations and calculate what should be average temperature of Earth's surface with our pen, paper and calculators, right, today, and we will see that what we got right, what we got wrong. So what is the most simplest thing we will make about Earth? We will say it's a dot, right? Of course, Earth is not a dot, it's an assumption. I will add elements to it later. Once I model something simple, then I will keep on adding complexities to that. It's a dot, it's a zero-dimensional object, right? No oceans because it's a zero-dimensional. No land because it's a zero-dimensional object. No air is flowing because it's a zero-dimensional object. So one assumption takes care of it all. Huh?
Can I have 5 minutes?
I'll just finish this slide and then we will have break before we go to pen and paper part, where we will not use slide, do calculations by hand. Nothing to worry. I'll be doing calculator math with you. You will just correct me if I do something wrong.
Did your former supervisor just give you a time
Yes.
sheet?
Yes. Today we are only interested in determining average surface temperature of Earth, right? Because with the problem we need to know what is the solution we are looking for, right? With this simple model you cannot answer a complex question that how much rainfall will happen, because the processes are not represented there. So we can only ask a very simple question with all these simple assumptions. And one thing is for sure, that we will not violate the fundamental laws of thermodynamics as and when applicable. With that, we will do our first calculation after the break, and we will see what we miss or gain if we keep our model simple, and how scientists go from here when things go wrong, how they are corrected iteratively until we reach the answer here. Okay, so we will have perhaps 8 minutes break. Alright.